Here is a mirror problem from the OpenStax College Physics textbook. It is an open source book, so I may post the solutions to the problem online. So the question asks, what is the focal length of a makeup mirror that produces a magnification of 1.5 when a person's face is 12 centimeters away? So we're going to use the method that we've used in the past in solving these problems. I'm going to start by writing knowns. So the things that I know in the problem are that the magnification is 1.5 and that the person's face is 12 centimeters away. So 12 centimeters away from the mirror, that is where the object is located. So 12 centimeters then is DO, object distance. Now, they're telling us that the magnification is 1.5, and we don't actually know if it's positive or negative. Sometimes problems tell you that, sometimes they don't. But if you're thinking about a makeup mirror, you want your face to be upright when you're looking in the mirror. So in this situation, the magnification is positive. Had the image been upside down, magnification would have been negative. But we're fine with what we have here, so we'll leave magnification as positive 1.5. The object distance, since the person's face is in front of the mirror, is also going to be positive. So remember, when we have a concave or convex mirror, I don't know which kind we have here, but they're not telling us that. The distances in front of the mirror are positive. The distances behind the mirror are negative. So object distance, maybe it's here or maybe it's there, but it's still in front of the mirror. So this would be our DO. Okay? All right. Next, we're looking for the unknowns in the problem, and we are asked to find the focal length. So we don't know what the focal length is. So thankfully for mirrors, we only have two equations. So one of them is 1 over f equals 1 over DO plus 1 over DI. And the other equation has to do with the magnification. So that is negative DI over DO. So we are given the magnification. We have that value over there. We're given the object distance, so that means we can solve for the image distance. And then from the image distance, we can plug that into, I guess I have an arrow here I can point at. So once we solve for the image distance, knowing magnification and object distance, we can plug the image distance here and solve for the focal length. So let's start with the magnification. So I know from here that image distance is negative MDO. So that is negative 1.5 times 12 centimeters. So that is, plugging into the calculator, negative 18 centimeters. So I have a value for the image distance. So let's stop and look at what this means. So image distance is negative 18 centimeters. Negative is on this side of the mirror. So we know that the image is virtual. And we already knew that actually because we knew that the image was upright. And remember that upright images correspond to virtual images. So this negative number just proves that indeed we get an image that is virtual, which in turn was upright. Okay? All right, now let's look at the focal length. So 1 over f is 1 over DO plus 1 over DI. 1 over DO was given as 1 over 12 centimeters plus 1 over DI, which is 1 over negative 18. And if I multiply this by 3, multiply this by 2, I have 3 minus 2. So that gives me a positive 1 over 36. So then the focal length is going to be 36 centimeters. What does this mean? It means that we have the focal length somewhere here, since the object distance was 12 centimeters and the focal length is 3 times that. So the focal length is somewhere here, right? And we get a positive value for the focal length, which means that the mirror we're using is concave. Had we gotten a negative value for the focal length, then we would have realized that the mirror was convex because the focal length is negative in a convex mirror.